Okay, shall we start the second morning session? The first speaker is Paolo Mazzali, who will talk Type 1b C supernovae and gamma ray bursts. Please.
Thank you very much. So I should thank both Thomas and Ken before for setting such a nice outline of this, which makes my job easier introducing this topic, which is a subset in the end of core collapse supernovae. But just for those who may not be so familiar, we've seen a couple of plots of this before. Why are we connecting supernovae and GRBs? There's two kinds of GRBs. The first couple of days of this meeting have all been focused on the shorts, and we heard a lot about neutron star mergers and so on. What we are talking about now is stuff that connects to, with the long and soft family, which is in number the overwhelming population of the GRBs detected so far. These tend to be longer with variable length, and there's things associated with them. And it's interesting to see how basically 20 years on to the day, history repeats itself in many ways. So we go back to the days of Beposax, which was a precursor of Swift and had kind of similar characteristics. And as soon as Beposax developed the ability to point to the location of these long GRBs, which are easier to locate because they last longer, the association with galaxies was immediate. And on about the second or third such association, this spot of bright light was detected, which made a further association. And of course, you expect that. You're now in a spiral arm. Remember Eleanor's talk, the short GRB connected with the gravitational wave signal was in a fairly anonymous spheroidal galaxy. This is now an irregular galaxy with spiral arms, with things. And this event happens on an arm, so which is a nice star-forming region. And Ken just described before the peculiarity of the spectra there. Back then, it was for some quite puzzling to see what the spectra looked like and to try and understand what they were. We do know now, and Ken briefly described that before, that if you broaden absorption lines, you get these big absorption troughs followed by these re-emission P Cygni peaks. And that's all we're looking at. But at the time, this was fairly new. This 1970 F event that Ken had described briefly was kind of similar to this. It was the first one ever seen a few months later, actually almost 20 years now. We should be celebrating this in April. The first long GRB supernova connection was actually identified. So what is interesting about these is to try and understand from the spectra what they tell us. And spectra contain a lot of information, as do LICOs, but spectra, I would say, even more so. This repeats, I think, a plot that Ken had before, just to highlight what kind of supernova we're looking at. What Thomas was talking about before is mostly, with the exception of Casey, where he just mentioned it's a 2b, so most of the hydrogen envelope had been lost. What we are looking at here is type 1 supernovae, where there is no hydrogen. And type 1s, for those who are not familiar with supernova zoology, divide into three groups, A, B, and C. Type 1As, you know from the cosmology, they have nothing to do with massive stars, they're white dwarfs that explode. The 1 stays with us because it means there is no hydrogen. So everything in astronomy makes no sense, and this is one of the many things that makes no sense. But the B and the C stand respectively for helium, and C for neither, or no helium, no hydrogen, but more intermediate mass elements like the silicon and iron lines, oxygen, calcium, so heavier elements than your hydrogen-rich or helium-rich events. The hypernovae, or broad line type 1c supernovae, are just an extension of the 1c family, where the kind of lines you see are the same, but they're broadened. And this is basically a Doppler effect. So it just means that the material moves fast. Lines broaden, they merge into big absorption troughs, and they give rise to these few re-emission peaks, which are not net emission, as some people still might be thinking, but certainly did at the beginning. They're just places where line opacity is weak and photons can escape. So you see a few features that are the combination of many absorption lines, many lines that are sort of overlapped by a velocity dispersion in the ejecta. So the broader the line that you see, the higher the velocity dispersion, which means the more velocity you cover in the ejecta themselves. And in all of these, this was 97 EF, and this is 90 ABW. So if this was broad, this is a lot broader. And this is the event that came with the gamma ray burst. So just to put things in context, again, these are massive stars. We know that from their origin, for example, their location. We know that from the fact that in many cases they contain hydrogen and helium. In the case of the 1Cs is more a location argument. So Thomas described the events and how these can be made to explode, and neutrinos play a significant role, as do asymmetries and so on. There's all this work in progress going on. But the long and short of it is they produce order of 0.1 solar mass of nickel-56, with some exception. And they would associate with red supergiants, 87A being an exception, unless you manage to remove the outer layers of the star. Then if you do that somehow, through either mass loss through a window, or more likely in the case of helium, binary interaction, then the star will not become a red giant, because it will only have its carbon and oxygen core to live with. This will not expand. And the progenitor of supernovae that we call type 1Cs and 1Bs are more likely to be the Wolf-Rayet type. Now, a direct connection has not been made, because these are very blue stars, and they're hard to find in images before explosions, which is one of the most commonly used techniques to identify progenitors. The technique is successful when you're looking at red supergiant, because, of course, those are bright spots in galaxies. But when you're looking at Wolf-Rayet stars, unless you've got very blue images, you're not going to pick them up in a stellar field. But that is a tentative association that is being made between progenitors and the supernovae. So if we go a little bit into what this stripped envelope, as the general name nowadays seem to be, these nomenclature keeps changing. You're proceeding physically from having a little bit of hydrogen left in the 2Bs, which will be the Cas case. So you've got some H alpha here, but not very strong compared to your red supergiant progenitors and the type 2P supernovae. Then you remove all the hydrogen and you see the helium shell first, and that will give rise to helium lines. If you manage to somehow remove the helium as well, then you have only the heavier elements that Thomas was talking about, the intermediate mass elements, the iron, and so on, and then you get this type 1C spectrum. Okay. So you can classify the 1Bs and 2Bs by the amount of helium and hydrogen that is left. But you can't do that with the 1Cs because you've got none of either. So you need to go into some other definition. This width of the lines is an interesting way of classifying type 1Cs because it actually is a proxy for energy. As an aside, depending on your favorite classification mechanism, there's about 50% 1Cs versus 50% 1Bs and 1Cs. You see, they kind of divide this way. Among the stripped envelope, half only have the carbon and oxygen core. This makes it a bit difficult for a single star model, because it's not obvious how a star so successfully loses both the hydrogen and the helium shell. But the other interesting comment you can make is by plotting light curves, and this is work done by students of mine, collecting basically all the possible reasonably sampled light curves of type 1Bs, 1Cs, and 2Bs, and you now plot them separately, where the 1Bs and 2Bs are on one side and 1Cs, regardless of line width, are on the other side, and you see a slight offset in luminosity, where the 1Cs are slightly more luminous, which means they produce more nickel-56, and they have a bigger spread. Okay? In red are some broad-lined events and GRB supernovae. And if you look at the average of those, it's a bit brighter than the non-broad-lined events. There's quite a lot of dispersion there, anyway, one should say. We're looking at this kind of event here. And I said you can use these properties to classify, and say you could do that between 1Bs and 1Cs. Is there a continuum let's start with 2Bs and 1Bs. 2Bs, remember, have a little bit of hydrogen. 1Bs have none. But there's events in between where the strength of the hydrogen line becomes weaker, which means you remove the hydrogen in different amounts. You always have very little, but you may have almost none, and then progressively a bit more. And this is probably of the order of 0.1 solar masses of hydrogen. If you have more than that, the star becomes a red giant. So you no longer have a compact projectile. So that is a way of classifying the 1Bs and 2Bs. And despite claims, we still don't really know the properties of all these supernovae. We actually don't have enough data to cover the range of what we see. So we now go down to the 1Bs, and we wonder why is the helium seen sometimes and why it is not. So one area that is debated these days, or has been for perhaps even too long, is the fact that sometimes we see helium and we call the supernovae 1Bs, sometimes we don't, and we call them 1Cs. And people say, well, we can't get rid of the hydrogen of the helium shell from a star if it is a single star. That is, that's what they omit to say. How do you get these helium lines? It's an interesting lesson here. This has been known for a long time, in fact. In order to excite these helium lines that you see in the optical and the near infrared, you need to excite levels that are 20 electron volts above the ground state of helium-1. This cannot be done by the thermal photons that give you the continuum of the supernova. Those are just too cold on average. You need non-thermal photons to do that, and you get those non-thermal photons from the incomplete thermalization of the gamma rays and the positrons resulting from the cobalt-56 and the nickel-56 decay. So you've got a population of non-thermalized photons there, which can actually efficiently excite helium if it is there. And then you bring electrons to these levels. From there, you can absorb into these lines, which are then the helium lines you see here. So could it be that you've got helium and you don't excite it, or could it be that you've got only 1Bs of helium and 1Cs don't? One way to see this is wherever there is helium in the optical, there is also helium in the infrared. So both helium configurations can actually be excited. Here there's been many claims that this line could be helium, but sometimes in the 1Cs you see a line here and you don't see its corresponding line in the different configuration of helium, the singular configuration. So it seems to us that whenever there is helium, you can actually see it. We can quantify that by making synthetic spectrum, by computing synthetic spectrum, where we take the diffusion and the position of the energy carried by these fast particles into account, and then we place different amounts of helium on top of the star and see whether the excitation works. The result of that is that with something of the order of, again, 1/10 of the solar mass of helium and a little bit of nickel in the deepest layers of the explosion, you do successfully excite the helium lines. Same thing is true, in fact, for the hydrogen, where it's enough to have a couple hundredths of a solar mass of hydrogen to see the H-alpha line that makes the supernova a type 2b. So that tells you something about the classification of these, and in my opinion at least, suggests that whenever you see helium, it's there. Whenever you don't see it, it's not there. So it's not that you're hiding it, because it's enough to have a little bit of nickel to actually produce helium lines. If we now want to go to something that concerns 1Cs, I said it's line breadth or width that mostly affects what these spectra look like. And here's a few examples with supernova names that we still can remember. In the last few days, perhaps, of being able to do this. We're already in 3-letter era, which makes it really difficult to remember anything, but these still are from the 2-letter era in the 90s and the noughties. And so these are all 1C spectra, and you can see that the basic feature that distinguishes them is the width of these lines. But if you can't even measure a line width, you can just count the number of lines you see. So this is really easy. And you just say, well, this has more lines than that. You don't even need to have a ruler to measure how wide the lines are. There's fewer of them. And there's fewer of them because they blend. And you can see the blending process going on. The trace of the line is still there. But while here you see, say, two separate lines, they start blending here, they have blended there, and they've been blended away here. So you kind of lose this information. You see here the iron triplet, for example. You can distinguish the three lines here. They start blending. They have blended, and now they're gone. But they are still the same lines affecting the spectrum. It's just that the Doppler shift within the supernova ejecta is bigger. So what is that telling us? It's telling us that these supernovae here, and this is your GRB supernova, have much higher velocities in the ejecta than those. And therefore, it tells you they carry more energy. And this is why I asked the question of Thomas before. When we go to a certain kind of explosions, we need to get high energy. And some of the game here has been to try and determine what that energy is from understanding these spectra. An important aside, and this is actually aimed more at the observers in the audience, is there's many attempts to determine the light curve, and from that to derive masses and to derive energies. It's all very well to get a mass from the width of the light curve, but you should not try and get an energy from it, because if you do not have information early on about what the mass is doing at the highest velocities, you will not be able to guess the energy. You will only get the energy that is in the lower part, in the lowest moving part of the ejecta, which is not very much compared to the energy you can store at high velocities, even if the mass involved is quite small. And the example here is play with an explosion model, change the density slope in the outer, the outermost points. You're involving a very small mass. The density scale is given here, so you can see you're a couple of orders of magnitude down from where the mass is. This changes the energy by a factor of about 3, and it changes the spectra from separating lines in the blue case where the density decreases to blending them in the case where the density is a bit flatter. And this has to be a property of how much energy you put in the explosion. And the message to the observer is these spectra are computed at about a week after the explosion, but we don't always get data that early. If we only get spectra, say, maximum light, so say 10 days, 2 weeks after explosion, they all look the same. Because the spectrum is now formed up here. The sort of pseudo-photosphere sits there. These levels are so thin, they no longer absorb any photons. That's why I'm saying for the light curve alone, you should not try and get a kinetic energy, because you probably, well, you just don't know. It's just a minimum value you can get. So very useful to get early information about the spectrum. So what we're proposing is to classify supernovae just by counting number of lines, which is easy. Everybody can do that. And then that turns roughly into a density slope of the outer layers, and therefore an energy, or at least an energy over mass of the supernova. The stars don't like to explode all the same way. So Thomas, with 6 months for calculation, has to postpone his retirement because we need more than 20 models. You're going to be around for longer, because even at the same line width, so take n equals 6, where you sort of measure 6 known lines in the spectrum, you have cases where the spectrum looks similar, but it's shifted by different amounts. So the average velocity is higher, but the spectral shape is the same. So you have a similar density slope, but a higher mass overall. So these are stars of different mass exploding with the same energy per unit mass, and so on. So you got at least a 2-dimensional space to explore. At 6 months per model, you need some time or faster computers. But we're very much looking forward to see if all this distribution can actually be realized. So let's go back to GRB supernovae. One thing that can be said about them is they stand out from the rest of the strip envelope crowd by being, on average, more luminous, which means they produce, on average, more nickel 56. They can be almost as bright as a type 1a supernova. Those are your favorite iron cauldrons. They make more than half a solar mass, on average, of nickel 56. The example here of 98 BW comes very close to that number, which is much bigger than the 0.06 that Thomas was mentioning before as your classical core collapse supernova yield of nickel 56. This is good because it makes them bright, so they're kind of easier to follow, both at early times and at late times. I've mentioned the width of lines as a proxy for energy. You can measure the position of some lines, or you can model the spectra and have a velocity to use as input for your models. And you plot that as a function of time for different types of supernovae. The color coding is a bit complicated, but the black dots here, 94I, is your classical low energy type 1c, while the red dots here represent GRB supernovae. And notice the difference in velocity at similar epochs. So you easily reach 0.1c at a week or so. So earlier on, you expect to form your photosphere at very high velocities in GRB supernovae. So you have more material at high velocities, therefore you have more kinetic energy. You can use a combination of light curve and spectral properties to kind of derive the masses involved. I mentioned how difficult it is to get kinetic energies without early spectra, but you can use that, and this goes back to our net a long time back, to, from the width of the light curve, determine roughly the mass involved. And of course, the mass depends a little bit on the energy you use, hence some degeneracy. Hence, if you don't know this, you're not going to know that very well, but you have some guess of what the masses involved are. And this is also both interesting and a cause for concern, because we know that the energy and the mass seem to have some kind of an interdependence. Let's just stop at 90 ABW and see what happened to it. You've got this light curve, and if you just fit a light curve model, there's many parameters that will give you a right light curve because E and M are degenerate. You have to look into the spectra, and we did that back in those days with Ken and his group. And spectra that are formed from models with different energies and different masses will not look the same because the energies will be different. So you try and find spectra that fit the width that you observe, and you end up with extremely large values of the kinetic energy. And so this is going to be somewhat of a challenge for these models to get. I mean, so far, I think people are being able to get to about 10 to the 51 ergs, and this is 50 times as much in spherical symmetry, but still it's several times bigger than the values that have been given. And the amount of nickel you make here is also something that is going to require quite a bit of energy. So what is going to be the pairing mechanism for these events? As I said, these supernovae are bright, so they're easier to follow for a longer time, and that allows us to monitor the so-called Nebula Phase, where the supernova ejecta become thin. They no longer reach an optical depth of 1. You can see through them, they look like a nebula, and you can now study the morphology through the shape of the emission lines, both the morphology and the composition. And the interesting thing to notice here, this is again 90 ABW between 4 months and a year after the event, is the spectra are dominated, and you should look at the narrow lines here, by this oxygen emission, which tells you that what exploded was a carbon-oxygen massive core. However, you've also got strong iron lines, which testifies to the fact that the supernovae produce a lot of nickel-56, but the iron lines are broader than the oxygen lines. So in a one-dimensional picture where you've got your onion shell structure for a star, and heavier elements sit deeper, you explode that, you're going to put a higher velocity in the lighter elements, which is the opposite as what we see here. So because we're not invoking huge overturn in the composition, this basically smells like a very asymmetrical explosion, viewed from a particular angle, and we know that that angle was special because we caught a GRB from this. And GRBs, okay, Zvi might argue about this particular one, but on average, we don't think they are that isotropic. What we think we've seen is an event looking kind of like this, where we're favorably located to see the GRB, and therefore we picked up the material where most of the kinetic energy was deposited. Along that kinetic energy deposition came the nuclear synthesis, came the nickel-56, and therefore we're picking up high velocity in the iron, which is the product of the decay of nickel-56. And we're picking up low velocity in the oxygen because the oxygen is mostly moving at 90 degrees from our line of sight. Therefore, that's going to give us narrow lines. And it's not an onion shell structure that does that. It's this sort of two-dimensional distribution. And the ratio of line width depends very much in this case on the orientation of the position from where you see an event of this kind. So that you can even predict that if you viewed this event from the side, you would see an emission profile like that for the oxygen line, because now you're looking along the plane where the oxygen is ejected, and you're seeing two blobs of oxygen, one moving towards you, one moving away from you. This was actually a prediction that was soon thereafter verified by observation. So there are supernovae that look exactly like these models had predicted. Was this a GAB supernova viewed way off axis? Quite possibly. There has been debate about this, but if this didn't have a GAB, others might. But in any case, the profile of the oxygen suggests that the degree of asphericity was actually quite large, in a way similar to what we thought for 98 BW, the GAB event. Is this telling us something about core collapse as a mechanism? Thomas talked about some instabilities. Is this generic? Is this sufficient? There's been quite a few pieces of work about looking at late time emission profiles, in particular these oxygen lines. And you can see that the distribution of line profiles goes from just your standard single broadish line to the double peak profiles, which have been seen a few times. And statistically, this is consistent with basically every type 1bc supernova being aspherical, and the distribution of profiles reflecting only your viewing angle. So if you're seeing them on the axis of asymmetry, then you see single peak profiles. If you see them 90 degrees from it, you'll see double peak profiles. You take a sample, and that's kind of like the distribution you would expect. And so this suggests that strong asymmetries are actually generic of the core collapse mechanism, at least when we don't have the hydrogen on top. There shouldn't be any interplay between the presence of hydrogen and what happens in the explosion, but we can't really get good enough data for the Type 2P supernova. There's just too much hydrogen around to see down to these shells. This issue of asphericity and higher energies does not just affect GAB supernova. There seems to be, as Ken showed before, some trend whereby higher energies and higher masses go together. So when your star is more massive, it explodes with a larger energy. This is an example of a type 1b supernova, so something that came with helium, seen with these broad lines and an accompanying X-ray signal, call it an X-ray flash, call it whatever you want. But the long and short of this is that the energy of the supernova was several times 10 to the 51 ergs, and the mass involved in the carbon-oxygen core was 6 solar masses. So we're talking of progenitors of maybe between 25 and 28 or 30 solar masses. So an enhanced energy for an enhanced progenitor mass. And if you look at this in the late time, there is indication in the spectrum here that the profile was also rather composite, indicating perhaps some degree of asphericity there as well. One thing, going back to Zvi's talk yesterday, this event may also have had a GRB, but it had a helium shell around it, which could have caused the jet to be choked, basically, and be blocked in the helium shell itself. And we did some work with Zvi in the past about that. So again, is this generic? Is this asymmetry generic? We've been lucky enough last year, well, actually 2 years ago now, but not end of 2016, to be able to observe a GAB supernova, and they don't come very often, as Eleanor said on Monday. There's one every about a couple of years, and it's not always favorably placed and so on. This was actually in a nice part, almost nice part of the sky. We could follow it for a long time. We could catch it very early. We actually measured velocities of well in excess of 0.1 c at the earliest times, because we actually could get on target with the VLT very early on. We get very similar values for this event as we did for 98 BW, which is also an interesting point. We measure these very high velocities. We follow the spectra for a long time in high detail, so this is much better covered than, say, 98 BW, allowing us to actually model the spectra with a lot more detail we can now look at the distribution of elements as a function of depth as we look deeper into the supernova as time goes on. So what happens is the supernova expands, the optical depth increases, and you can look deeper. So you can actually track the composition, energy, morphology of the event as a function of depth. What we came up with here is that we seem to have spotted a decrease of the nickel abundance with decreasing velocity. So there's more nickel outside than there is inside. Okay, so this is, think about it for a minute. You produce the heaviest elements near your mass cut, near where you make your remnant. You may put some in a jet and put them out at high velocity. If you did that, you might end up with a situation where the heavier elements, such as the nickel 56, are at a higher velocity than lighter elements if your viewing angle is favorable. So in this sort of cartoon, I'm trying to show the fact that if you view this event right along the GAB jet, you see a nickel-rich region made in the highly energetic part of the ejecta. And you see that better early on because it covers a bigger fraction of what you see of the supernova, which is basically down to, say, here. Sometime later, you see down to there, and you start picking up the oxygen-rich sides of the ejecta. And so your oxygen abundance as a function of depth, and depth is only along this direction, seems to increase because you're picking up more of the lateral material. Okay? So if this is correct, there's a lot of uncertainty about the models and about the data reduction and about a lot of things, but it seems to be the best model. If this is correct, then we may have seen another way of picking up this abundance inversion, whereby by exploding stars with a high energy that is focused in a particular direction, you actually reverse the process and put heavier elements on the top and possibly help create a GAB on the axis of the explosion. This is something that Ken showed before. Maybe it's one of the latest versions of this, where the GAB supernovae are the most massive and most energetic events, and other events sort of crowd at lower energies and lower mass, but indicating some kind of trend where by increasing nickel mass, you increase kinetic energy, and by increasing ejected mass, which now stands as a proxy for progenitor mass, you also see an increase in kinetic energy. So if we go to massive stars, at least the ones we do see, the ones that do explode, you need to have more energy. This more recent event, 2016 JCA, that's why I'm saying it's becoming difficult to remember their names, sits right in between all the ones that have been seen so far. There is a kind of repeatability of the phenomenon. Every GAB supernova seems to cluster at these values of mass, energy, and nickel mass. There's not a lot of diversity compared to the diversity of the standard sort of core collapse from 87A to the 1Bs and 1Cs and so on. GAB supernovae are only there. So what is actually going on? Something we did a couple of years ago with Stan Woosley and Andrew McFadyen was to look at the GABs and look at the supernovae and try to see how we can connect one and the other. The word is, GABs carry quite a bit of energy, but the supernovae here carry a lot more of the energy. So the kinetic energy of the supernova is shown here, the kinetic energy of the GABs in isotropic approximation. So you only measure the distance and multiply what you get by 4 pi is anyway smaller. You can then correct for the beaming angle of the GAB, bringing down the gamma ray energy to values that are a lot smaller than the supernova energy. So the energy is actually in the supernova. It's not in the GAB. The GAB is only like not even 1% of the energy that is produced. So you cannot really say the GAB explodes the star and drives all this, because the GAB has no energy compared to the supernova itself. How can you actually pass 99.9% of the energy onto the supernova explosion? The other thing you can notice is that supernova energies, as I said, these are very similar, and they cluster at values of a few times to 52 ergs. And these are spherically symmetric estimates. They may go down a bit, but they still do cluster around a fairly narrow range of values. you can do the same game in the radio, and you kind of show that the radio follows the GRB energy rather than the supernova energy, but that's a different story. But the important thing here is the supernovae, the carried GRBs, have a very large energy, and that energy is roughly constant. And that is in line with, actually, the limiting energy you can get from a magnetized, rapidly spinning neutron star. There's no, direct connection between them, but that seems to be in the right range. That's about the energy you can claim. If energy is constant, then this could be one reason that the energy could be constant. Maybe it's a magnetar is at play here rather than the collapsar model feeding energy into a black hole. And when we talk about a magnetar here, we are not trying to explain the supernova light curve with the magnetar. So when you've seen the plots in Ken's talk before, this is magnetar injection of energy over a long time causing light. This is what we're talking about here is magnetar energy that is injected quickly and actually energizes the supernova. The light comes from nickel 56. So the magnetar can do many things. What we're saying here is the magnetar can be used because it has the right energy to energize GRB supernova events. I've stolen this from Eleanor's talk because there's a very interesting historical connection here. Of course, Twee saw it as well as I did and stole it too and put it there. But this is the GRB that went with 98 BW, so 980425. And this is 170817. And look at where they are compared to the vast cosmological population of GRBs, right along the extension to very low energies. Hence, that connects with what Twee was saying yesterday about how special both of these events may be actually in a similar way, because they don't seem to be very much collimated either of them. So history repeats, in a sense, and we should use that to make faster progress. But let's go back to magnetars here. And have we seen evidence for magnetars elsewhere? Nowadays, it's popular to fit just about anything that goes up and comes down with a magnetar. But this is the assumption that magnetar energy is turned via collision into light. This may have happened in this particular case, which remains a unique case of 05BF, where the supernova reached a maximum, which was nothing special. You would never have noticed this supernova in particular, except that instead of just decaying away, it then rose to a second, very bright and quite late peak, which you cannot fit with nickel 56, because then you would expect, regardless of how you make nickel 56 at a later time, you would then expect to decay on the cobalt line, and you don't. You actually go back down to where you would have come if this had been your peak. So this extra burst of light, if you so wish, is due to something else. It's not radioactivity. And a magnetar injection of energy, something that injects energy on the time scale of about a month, seems to be the right, one of possibly the right solutions. Magnetars have also been invoked to explain supernovae that sit in between GRB supernovae here and your lower energy core collapse events, producing more nickel and increasing the energy of the explosion. So we're talking about magnetars now again being used very early on to make energy, not to make light via collision. I'm never going to go into that particular area. But this is something that has been mentioned as a possibility in order to enhance the amount of nickel 56 and make this supernova brighter. This came with an X-ray flash. So there is some interesting connection there, perhaps, as well. And the values we derived are shown here. Couple solar masses of the ejecta, twice 10 to 51 Earths, and I believe that is going to be a challenge itself for neutrino-driven models alone. And a significant enhancement in the production of nickel 56. Finally, there has been just a passing mention of ultra-long GRBs and a possible association with supernovae. So I'd like to spend a couple minutes talking about that. There's only like half a dozen or fewer known, depending on what you call what, ultra-long GRBs, so things that last 10,000 seconds roughly. In one case, a spectrum was taken. The spectrum is shown here. It's admittedly noisy, but it is also rather featureless. So you don't see a lot of absorption lines. Is it a supernova, or is it something else? This particular group of supernovae called superluminous, which have also been mentioned in passing and not in great detail, tend to show similar spectra, not a lot of features. And they're still known as supernovae because they go up and come down, and they're associated with stars, and they start looking like type 1c supernovae later on as they decline. These are also a spectra around peak. The event, if you want to call it a supernova, associated with this ultra-long GRB here, sits in light curve right in between GRB supernovae and superluminous supernovae, again offering a low energy, low luminosity connection, perhaps. And you can actually model the spectra with stellar ejecta and a rather low specific energy, where the energy per mass is not particularly high. You can actually blanket out the various lines and get a very hot continuum because the luminosity is very high. Which takes us to how you make the spectra of these superluminous supernovae. They're so bright, you ionize away the species that you see in the 1Bs and 1Cs. What you do see is lines of oxygen 2. And people have been puzzled by the presence of oxygen 2 lines. It's primarily a temperature effect because you've ionized away other species, which we'll then be seeing later. But you also need to understand that you don't get oxygen 2 lines easily. Oxygen 2 is as bad as helium 1 or worse. So this is the plot I wanted to show you. This is a Grothian diagram of oxygen 2, which shows you where the various levels are. The oxygen lines we're talking about are created in levels that are, again, more than 20 electron volts above the ground state. So you do not excite these levels thermally. You do need some non-thermal radiation or particle population to populate these levels. So it's exactly the same process at play that you see in the type 1b supernovae, except it's even harder here to excite the lower levels. Once you do that, you go back to these, and all of your lines come out quite nicely. So once you understand the mechanism, you probably understand a lot about what's going on. So one idea here is that potentially there is something creating X-rays, and magnetar impact could be doing that, and that might populate the lower levels. So one is expecting to see detections of X-rays if they penetrate through the envelope and get out from superluminous supernovae. That might actually confirm what we are seeing here. Otherwise, the composition of these things is exactly the same as 1Bc supernovae. Carbon, oxygen, sometimes some helium, and no hydrogen. So there's a lot of similarity, and one actually wonders what the pairing mechanism of the superluminous supernovae actually is. It may be too much to ask for just nickel 56 to be doing this, but magnetar energy might actually be one of the ways that you do this. And another point in favor of this is that the velocity evolution of a superluminous supernova like this is a classical event, is rather flat over time. While supernovae like 98BW decay in velocity very quickly as the photosphere moves inwards. In this case, the photosphere hardly moves, as if it is being supported by something that pushes from behind. So the densities don't drop very quickly. And normal stars don't do that. So while there are similarities, there are also differences one would like to understand. So just putting everything together, and we're coming to the last couple of slides, the typical energies and masses of these events are shown here, where we go from the low energy 1Cs to the broader lines 1Cs to the GRB supernovae. The ejected mass goes up. The kinetic energy goes up a lot, so that this ratio of energy and mass, which determines the spectral shape, also increases. The superluminous supernovae do exactly the same thing. While the masses can range from high to low, and we don't really have a good enough sample to cover the whole range, E over m goes up. In the ultra-long connected case, it's a value larger than 1, while in the normal case, it's a value close to 1, explains what we see. So there's a lot of similarities there, as I said. And if we actually put the ultra-long event here, did I put it there? Yes. So this is where superluminous supernovae fall in this diagram. They have larger mass, but not particularly high kinetic energy, the GRB connected, the ultra-long GRB event is actually here. And it stands in a different place from the normal superluminous supernovae, but you have a larger kinetic energy over mass, basically. So can you explain all of this? Can we try to put this into a single picture? This is basically copied from something that Brian Metzger likes to show, which is kinetic energy, magnetic field strength and spin period of a magnetar that can power different events. So we've played a game here of saying, well, we want to extract the energy quickly if we want to power up an event like GRB supernovae. We want to extract the energy at a later time if we just want to power the light curve later on. We end up with magnetar parameters here of magnetic fields between 10 to the 14 and 10 to the 17, which is admittedly quite high, and spin periods in milliseconds that are of the order of 1 to 0.1. So a range of magnetar properties may explain these events, which are a minority, of course, of all the core collapse supernovae. So to put it all together, if we want to believe this picture, we need fairly massive stars, and the mass needs to be determined taking these new sort of understanding of the remnant properties into account. But you need fairly massive stars to create GRB supernovae because we see 10 solar masses in the ejecta, and that is carbon-oxygen core of a star. So you need order of 35 to 50 to get there. If you're not as massive, you can still enhance the kinetic energy and the nickel production, possibly by forming a magnetar. And there is some correlation between the mass of nickel, the ejected mass, and the kinetic energy of the explosion. And finally, the superluminous supernovae share many of the properties of 1BCs. I think I'll stop here. Thank you very much.
Okay. Thank you very much. We have time for one question. Yes, please.
So if you're, for the superluminous supernovae, if you're arguing that the O2 is coming from some kind of underlying X-ray source, I mean, how much luminosity do you need? At what point do you expect that that is eventually going to escape?
It should escape at some point unless the magnetar decays over a longer time. So we should be seeing it. The energy required is you need to populate these levels with the same kind of energy that a solar mass of nickel-56 would give you. So you work that out. But if you just produce X-rays, then you'll be favored in doing that. But one would actually need to simulate it properly. We just so parameterize it here.
Okay. Let's thank the speaker again.